Namaskar. So, in last two sessions we discussed about three phase connections, especially star star, and then we discussed star delta connections, and then in the last lecture we discussed about the delta delta connection. So, today we will start our session with the delta star connection. You can also say delta Y connection, where delta is the source and star connected is the load. And we also in the later part of the session we will discuss about the energy for a three phase system. So, let us start our discussion. So, basically in case of delta Y connection or delta star connection, we have source delta connected and the load star connected. So, if you see in this figure, the source is connected in delta and the load is connected in star, and the line currents are IA, IB and IC. Now, as we discussed in the previous cases, in this case also we assume that the positive sequence is considered for the source, and the phase voltage of delta connected source can be given as VAB is equal to VP angle 0 degree, VP is RMS value of the phase voltage. Similarly, VBC can be given as VP angle minus 120, VCA can be given as VP angle 120 degree. So, as you know, in case of delta connected source, the line voltage and phase voltages are same. Now, let us apply KVL to find out the line current. How we will find? Let us consider the figure which we saw in the first slide. Now, we will apply Kirchhoff voltage law around the loop, that is small a, capital A, N, capital B, small b and small a. So, this will be the loop in which we will apply the Kirchhoff voltage law. So, if we apply, we start with B. So, we can write minus A B, then Z y into I A minus Z y into I B equal to 0. So, we can rearrange it and say that Z y into I A minus I B equal to V A B, which we can conveniently write V P angle 0 degree, or I A minus I B is equal to V P angle 0 degree divided by Z y. Now, as we know that I B lags I A by 120 degree, we can write I B is equal to I A angle minus 120 degree. If we put the value in I A minus I B, we can write I A in bracket, we get 1 minus 1 angle minus 120 degree. So, if we change phasor into the rectangular coordinates, you can write the term in the brackets as 1 plus 1 by 2 plus j times root 3 by 2 multiplied by I A. So, if you take root 3 out from the bracket, you can write I A into root 3, and then in the bracket you will get root 3 by 2 plus j times 1 by 2, which you can simply represent with angle 30 degree. So, you get I A minus I B is nothing but I A root 3 angle 30 degree. So, if you put the value of I A minus I B in this expression and simplify, you get I A is nothing but V P by root 3 angle minus 30 degree divided by Z y. So, in this way you can calculate the line current for delta star connected system. Now, another way to obtain the line current is that you replace the delta connected source into its equivalent star connected or Y connected source. So, when you convert, let us say that the phase voltages are VAN, VBN, and VCN, and we have already discussed that line voltage of Y connected source leads their corresponding phase by 30 degree and and root 3 times the magnitude. So, in that case what you can write, VAN you can simply write as Vp by root 3 angle minus 30 degree, because now you have converted into equivalent star connected source. Similarly, VBN you can write Vp by root 3 angle minus 150, VCN you can write Vp by root 3 angle 90 degree. Now, in case if you have a delta connected source with some source impedance ZS, in that case you can apply star delta transformation and find out the per phase source impedance for equivalent star connected source. In that case your source impedance will become ZS by 3, as we have already seen when we were doing the star delta transformation. Now, once the source is transformed into Y or star, the circuit becomes YY network, which can be easily solved using single phase analysis, which we have already discussed. Now, let us take one example. Suppose if balanced star connected load is having impedance of 40 plus j25 ohm per phase is connected to delta connected positive sequence source having VAB equal to 210 angle 0 degree. We need to calculate the phase currents and line current. So, we have load impedance as given, we converted into phasor format, that is 47.17 angle 32 degree. Now, the source voltage is given as VAB equal to 210 angle 0. We will convert delta connected source into star connected. So, in that case per phase voltage for a equivalent star connected source will be VAB by root 3 angle minus 30 degree. So, if you simplify you will get 121.2 angle minus 30 degree as the per phase voltage. Now, what will be the line current? Line current will be simply VAN divided by ZY. So, if you put the value of VAN ZY and simplify, you get IA is nothing but 2.57 angle minus 62 degree ampere. Similarly, IB and IC you can calculate as 2.57 angle 178 degree and 2.57 angle 58 degree. Since the load is balanced, so magnitude of currents, that is line currents, will remain same, the only change will be the angle value. Now, let us discuss the power in the balanced 3 phase system. So, to find the instantaneous power absorbed by any load in case of the 3 phase system, we will do the analysis in the time domain. So, what we will do? We will assume that we have the load as star connected. The phase voltage in that case you can say VAN is equal to root 2 times Vp cos omega t. We have added root 2, why? Because Vp is in RMS value and the term which we see before cos is peak value. So, we multiply Vp by root 2 to get the peak voltage for the VAN. Similarly, for VBN we can write root 2 Vp cos omega t minus 120 degree, VCN we can write root 2 Vp cos omega t plus 120 degree. Now, if load is ZY, we can write it as Z angle theta. The phase current will lag behind their corresponding phase voltage, in that case by angle theta. So, what we can write? The currents IA you can write as root 2 IP cos omega t minus theta, IB will become root 2 IP cos omega t minus theta minus 120 degree, IC will become root 2 IP cos omega t minus theta plus 120 degree, where again here also we are assuming IP as the RMS value, that is why root 2 we are multiplying in the RMS term. Now, total instantaneous power in the load, you can say the total instantaneous power will be the sum of individual phase instantaneous powers. So, we can write the total power instantaneous power P is nothing but P A plus P B plus P C. Now, what is P A? P A will be V A N into I A, P B will become V B N into I B, P C will become V C N into I C. Now, we will put the values of V A N I A, V B N I B and V C N I C, and we will see there are some trigonometric terms. So, 2 V P I P will be the constant term, we can take it out. Inside the bracket we will get cos omega t into cos omega t minus theta for V A N I A term. V B N I B will give you cos omega t minus 120 degree into cos omega t minus theta minus 120 degree. So, this will come from the voltage and this will come from the current. Similarly, for C phase you will have the cos omega t plus 120 degree multiplied by cos omega t minus theta plus 120 degree. Now, we will use this trigonometric identity which says that cos A into cos B is equal to nothing but 1 by 2 cos A plus B plus cos A minus B. So, if we use this in the above expression, what we can write? We can write P is nothing but V P into I P. In the bracket you will get 3 cos theta plus cos 2 omega t minus theta plus cos 2 omega t minus theta minus 240 plus cos 2 omega t minus theta plus 240 degree. Now, let us assume alpha as a new variable which is equal to 2 omega t minus theta. The above expression will be simplified to V P into I P. In bracket you will get 3 cos theta plus cos alpha plus cos alpha into cos 240, because here this will become cos of alpha minus 240. So, if you expand you will get cos alpha cos 240 plus sin alpha sin 240. Similarly, for this term you will write cos alpha cos 240 minus sin alpha sin 240. Now, if you further simplify you will get V P I P, and in bracket you will left with only 3 cos theta because these two terms will cancel out. So, the total instantaneous power for a 3 phase system you will get 3 times V P into I P cos theta. Now, if you see this expression, what you can observe? You can observe that total instantaneous power in a balanced 3 phase system is constant. That means, there is no time factor coming in this particular expression. So, even your instantaneous power of each phase will change with respect to time, the 3 phase power will remain constant. Now, since the total instantaneous power is independent of time, you can say the average power per phase for a delta or star connected load will be P by 3. So, per phase real power you will get as V P I P cos theta. Similarly, if you calculate the reactive power component, you will get Q P is nothing but V P I P sin theta. Therefore, you can write apparent power is nothing but S P into I P, S P is equal to V P into I P, and the complex power which includes real and reactive both component, we will write S P is nothing but P P plus J Q P, which is nothing but V P into I P conjugate. In this case here V P and I P are the phase voltages and phase currents, and V P and I P is the magnitude of the phase voltages and currents. Now, for 3 phase system, total power P is 3 times of the power in each and every phase. You can write 3 V P I P cos theta. If you convert phase voltages into line voltages, you will write V P is nothing but V L by root 3, and in that case you can write total power in terms of line voltage and line current will be root 3 V L I L cos theta. Now, in case if you have star connected load, your phase voltage, phase current will be equal to line current, and line voltage will be root 3 times of your phase voltage. Whereas for delta connected load, your line current will be root 3 times of the phase current, and phase voltage will be equal to line voltage. So, what we can say, irrespective of the load, whether it is star connected or delta connected, your total power will remain equal to root 3 VLIL cos theta. Similarly, the reactive power will also be equal to root 3 VLIL sin theta, and the complex power you can write as 3 times, that means for the complete system, if SP is per phase, then total complex power will be 3 times of SP, that is 3 times of Vp into Ip conjugate, or you can simplify it and you can get as 3 into Vp square by the load Zp conjugate. Now, if Zp is equal to the load impedance is represented as Zp angle theta, you can simply represent the complex power S as root 3 VLIL angle theta, where VLIL is the RMS value of line currents and VPIP is the RMS value of phase currents and the voltages. The major advantage of 3-phase system for power distribution is that the 3-phase system uses lesser amount of wire than the single phase system for same line voltage VL and same absorbed power PL. How? Let us try to find out and justify that the 3-phase system for power distribution will use less amount of wire when we compare with the single phase system, which is having the same line voltage and same power being fed to the load. So, what we will do, we will first assume that in both of the systems, one is 3-phase and another is single phase system, in both of the systems we are using the same material, that means copper with the same resistivity and same length of the wire is being used, let us say its length of the wire is L, and for simplicity we will assume that the load are resistive, that means the load is having unity power factor. Now, in case of single phase system, what will happen, we will have 2 wire create the single phase system, where one single phase source will be supplying power to the load. Let us say that the power being supplied to the load is PL and the voltage across the load is VL, and current which is flowing in the load is IL. R is the resistance of the transmission wire. So, what will happen, the power loss in 2 wires, because we are having 2 wires for creating the single phase circuit, loss in the transmission will be 2 times of IL square into the R. So, what we can do, we can replace the value of current IL as PL square by IL square will be PL square by VL square into 2 R will give you the power loss in the single phase system. Now, let us take the 3 wire 3 phase system. In this, let us assume that IL dash is the current which is going to the load. Here the amount, that is magnitude of all line currents will be, we are considering at same, and because we are considering the load is balanced. So, IL dash can be given as PL by root 3 into VL. So, in that case the power loss in 3 wires, because for the 3 phase system we will have 3 wires, let us assume that the resistance of each wire is R dash. So, the power loss in the case of 3 phase system will be 3 times the resistance of the wire R dash into IL dash square. Now, IL dash can be replaced by PL by root 3 VL. So, after simplification your loss, power loss in case of 3 phase system will become R dash into PL square by VL square. Now, from these two equations what we can say, P loss by P dash loss equal to 2R by R dash. So, P loss is for single phase, P dash loss is for 3 phase system. So, we say the ratio between P loss by P dash loss equal to 2R by R dash. Now, resistance R of the wire in case of single phase system, we can write rho L, that is the length of the wire, divided by pi R square. Similarly, for R dash we can write rho L upon pi R dash square, where R and R dash are the radius of the wires. So, if you put these value in this equation, you get P loss divided by P dash loss equal to 2 times of R dash square divided by R square. Now, if the same power loss is being tolerated in both of the system, means whether it is single phase or 3 phase system, the total loss in the system is same. That means P loss will be equal to P dash loss. So, when you say P loss equal to P dash loss, that means that R square will be equal to 2 times of R dash square. Now, the ratio of material required is determined by the number of wires and their volumes. So, what we will try to find out? We will try to find out how much material is required to create the single phase system as well as 3 phase system. So, material for single phase means, since we have 2 wires in the single phase, you can write 2 times of the wire. We are having wire as cylindrical in shape. So, the total volume will be pi R square into L, and then material for 3 phase, since we have 3 wires, we can write 3 times into pi R dash square into L. So, the ratio which we get is 2 R square divided by 3 R dash square when we compare the material for single phase divided by material for 3 phase. Now, from the loss comparison we already stabilized that R square is equal to 2 times of R dash square. So, if you put this value in this expression, what we get 2 R square upon 3 R dash square, the ratio will be 2 by 3 we can take out, R square divided by R dash square will be simply replaced by 2. So, we will get the ratio, that is material for single phase to material for 3 phase is equal to 1.33. So, what you can observe now? You can observe that the single phase system will use 33% more material than the 3 phase system to supply the same amount of power and to incur the same loss in the transmission system. Or you can write alternatively that the 3 phase system will use only 75% of the material as compared with the equivalent single phase system. So, this shows that in case of 3 phase system we need considerably less material to deliver the same power when we compare with the 3 phase system and the single phase systems. Now, let us take one example to understand what we have discussed with in relationship with the power. Let us see, there is one circuit as we see in the figure. We need to determine the total average power, reactive power and complex power at the source and at the load. So, here if you see, the source is star connected, the per phase voltage is 110 angle 0 degree for phase A, for phase B is 110 angle minus 120 and for phase C it is 110 minus 240. 5 minus J2 ohm is the impedance of the transmission line and it is same in all the 3 phases. Load we can see it is star connected again, where the per phase impedance of the load is 10 plus j8 ohm. Now, from this figure you can observe that the system is balanced. So, in that case, if you calculate the value of current I p, what you can do? You can simply use the Kirchhoff voltage law in the loop and find out the value of current I p. So, when you solve it, you will get this anyway is given in the question that V p is equal to 110 angle 0. I p you will be able to calculate, which will be equal to 6.81 angle 21.8 degree. So, this will be your per phase current. Now, in when you have V p and I p calculated, you can find out the complex power absorbed at the source. Now, since you know that source generally supply powers to the load, so if you ask if you are asked to find out the power absorbed, that means you will have negative sign in that. So, total complex power absorbed by the source will be equal to minus of 3 per phase voltage V p into I p conjugate. These two values you already have. So, when you put those values and simplify, you will get the source power absorbed, and when you simplify you will come to know that the real or you can say the average power absorbed at the source is minus of 2087 watt, while the reactive power absorbed is minus 834.6 VAR. Now, at the receiving end, means at the load end, ZP is given, you can convert it into phasor, that will become 12.81 angle 38.66 degree, and IP is given, that is line current also, because in case of a star connected, phase current equal to line current. So, complex power absorbed by the load you can simply calculate by this particular formula, that is 3 times I square into ZP. So, being a square term, you can simply write the square of the magnitude of the current. So, you will write 3 into 6.81 square into ZP. ZP you have calculated, that is 12.81 angle 38.66 degree. So, you get SL is nothing but 1392 plus J times 1113 volt ampere. So, what you can write? The real power absorbed by the load is 1392 watt, and the reactive power absorbed by the load is 1113 VAR. Now, the difference between two complex powers is absorbed by the line impedance, that means the power supplied by the source minus power absorbed by the load. So, what we will do? We will first find out the value of power absorbed by the line with the help of this formula, that is 3 times of I square into ZL. ZL is already given. So, if you put the values of IP and ZL and simplify, you get SL is nothing but 695.6 minus J 278.3 volt ampere. So, this will be the amount of power lost in the transmission, which will be nothing but the difference between the source power minus the power absorbed by the load. So, in the nutshell, what you can say, that the sum of the total power, that is source power plus load power plus power absorbed by the transmission line, will be equal to 0. So, with this we can close our today's session. In this session we discussed about the last combination, that is delta star combination for the 3 phase circuit, and also discussed about the balanced 3 phase power. In the next session we will discuss unbalanced 3 phase system and the calculation of power for the unbalanced 3 phase system. Thank you.